Okay, so let's look at this object over here. We have 4 objects that, I mean, at least if this equation is correct, they have to be a 4 vector. But let's see if they are actually, they form a 4 vector. So to say that they are a 4 vector, well, there are basically 2 strategies. Either we can look at how they transform from one reference frame to the other reference frame. So that was one of the parts in your midterm. Or we can just write them in terms of something else which we know is a 4 vector, times some number. So that is what we will do now. Now let's look at how the charge density changes from one reference frame to the other one. I mean, for simplicity, I will just assume that I have a very small charge. Let's say this is in a reference frame in which I have a very small charge element which is moving with a velocity v. And it has a charge density, let's say rho. And it is so small that all the points, all the charges in this volume element, they are moving with the same velocity v. So now if I start moving with the velocity v, in the new reference frame it will be at rest. So this is at rest. It has a charge that it corresponds to a charge density rho 0. And it has a volume v0. Here we have a volume v. And there is a total charge is q. Here the total charge is also q. So rho 0 is nothing but q over v0. And here in the initial reference frame, rho is nothing but q over v. But v and v0, v is nothing but the Lorentz contracted volume element. So here that it is at rest, it has some, let's say, in this direction, it has some length. And the v0 is the cross-section, perpendicular cross-section times that length. Now, if I go to this reference frame, if I start moving relative to that one, the perpendicular cross-section will not change, but the length in the direction of the velocity will get Lorentz contracted. So v is smaller than v0 by a factor 1 minus q squared over v squared over c, by a factor 1 over gamma. So this is equal to q over v over gamma. So rho is just rho gamma times rho 0. Or rho 0 times 1 over square root of 1 minus v squared over c squared. Now the corresponding current is just rho times v. Or this is equal to rho 0 v over square root of 1 minus v squared over c squared. Now you see, if you remember, we had defined a quantity that we called eta. Eta mu as dx mu by d tau. Now x0, it just turned out to be, well, d tau is dx mu divided by square root of 1 minus v squared over c squared dt. So x0 is nothing but c divided by square root of 1 minus v squared over c squared, eta 0. The space components is just dr by square root of 1 minus v squared over c squared times dt, or v over square root of 1 minus v squared over c squared. And we know that this is already a 4 vector eta mu, because x mu is a 4 vector. The difference of two 4 vectors is itself a 4 vector. D tau is just a scalar. So a scalar multiplied with a 4 vector is a 4 vector. Eta mu is a 4 vector. Now in terms of eta mu, rho is nothing but rho 0 over c times eta 0, and j is just rho 0 times eta. Or rho c and j, they are equal to rho 0 times eta 0 eta. But eta 0 and eta, they just form a 4 vector. This is just a number. A number times a 4 vector is a 4 vector. Now, of course, this we had derived for a special case where we were considering a very small, now where is it? Yeah. We were considering a very small charge element that is moving with a velocity v. In general, we have just a combination of these things, but that combination, that an expanded charge distribution, I can always divide in terms of very small charge and current densities. And the total charge and current density is nothing but the sum of the charge and current densities of each one of those small bits. Since the charge and current densities of each one of those small volumes is a 4 vector, the total charge and volume density, charge and current density, is the sum of 4 vectors, but sum of 4 vectors is always a 4 vector. So this kind of proves that whatever rho and j are, rho c and j, they form a 4 vector.
Ama şimdi lambda c dersek orada akım olacak, akım vektör değil.
The current density. You say if you have a linear charge density as in the book, lambda as it's moving, there will be, rho is a volume charge density, j is a current density, so there will be, the current will be on that line, but you can still write down a current density. Now there's one kind of, here our argument was the Lorentz contraction, so the volume in one reference frame was different than the volume in the other reference frame. But this argument kind of breaks down if you think about point charges. The point charges do not have a volume. So how do we get this transformation property of, even for a point charge, this should still be true. That is satisfied even for a point charge, although this argument does not work. In that case, we have a different argument. Let's do also for a point charge. No? No. Let's see how that comes about. There will still be a gamma factor. You see, in the rest frame of the point charge, let's say it is at the point x0, y0, z0, a charge q. So the charge density is q times Dirac delta x minus x0, y minus y0, z minus z0. Let's look at it from the moving frame. It's moving in the x direction. Q, x0, y0, z, well, let's say x1, y1, z1. And rho is still q times Dirac delta x minus x1, y minus y1, z minus z1. You see, it's exactly the same q. The total charge is still q. And okay, let me put these x prime, y prime, z prime. Well, you see, y prime is equal to y. Z prime is equal to z. But x prime gamma times x, or 1 over gamma times x. It's 1 over gamma.
Why not gamma times x minus v?
Yeah, let's say I'm looking at t equal to 0. I'm just basically considering these lengths, distance from the, let's say they are at, I'm looking at the t equal to 0, their origins overlap at that time. And similarly, x1, now y1 is equal to y0, z1 is equal to z0, x1 is equal to gamma times x0. Is it gamma or 1 over gamma?
1 times gamma.
Is it gamma or 1 over gamma?
Gamma.
Why? Well, you see, what is x1? x0 is this length measured in this reference frame. Here we are moving, we are in a different reference frame in which the chart, that reference frame is moving, so the length is contracted. The corresponding length, here this is x0, here I should have a smaller length. That smaller length is 1 minus v squared over c squared square root multiplied with x0. x1 should be equal to square root of 1 minus v squared over c squared x0. x0 is measured in this frame. That is Lorentz contracted, and we get x1. So 1 over gamma. This is rho prime. Now rho prime is equal to q x minus x0 over gamma, y minus y0, z minus z0, which is gamma q x minus x0, y minus y0, z minus z0, so it's gamma times rho. It is still multiplied by gamma, even for a point charge. The reason is not that q changes, it's just the coordinates change. That's why here I use the fact that Dirac delta of x minus x0 over gamma Dirac delta of x minus x0. Well, you see, motion is always one-dimensional. Let's say your particle is moving in this direction. Okay, why do you choose the x, y, and z axis like this? If the motion is in that direction, then choose your x axis in that direction. So it's one-dimensional.
Because you're very
At a given instant, its velocity is this one, or this one. Here I'm looking at a single instant. At that instant, it has a velocity in one dimension.
Why is the last expression like this? I mean, when the gamma is in the denominator,
Well, the Dirac delta has this property. So you just, if there is a function inside the Dirac delta, first of all, you find all the values of x that make that function 0. And then the Dirac delta you can just write as sum of Dirac deltas, each one having a 0 at this point, and then you divide by the derivative of your function at that point by its absolute value. So basically here gamma, what I'm doing over here is not really multiplying by gamma, but dividing by 1 over gamma, which is the derivative. Here I also have an absolute value, but I already know that gamma is a positive number. So kind of this completes my proof that this is a 4 vector. Okay, we didn't look at how it transforms, but since we already know that it's a 4 vector, we already know how it transforms. Rho C, rho prime C in a new reference frame, this will just be gamma rho prime C minus V over C Jx. J prime x will be just gamma Jx minus V over C rho prime C. Jy prime is equal to Jy, Jz prime is equal to Jz. And x is that I chose my x direction as the direction of the velocity of my new reference frame.
Hocam sınavdan önce sevdiniz.
Hocam, I think there is gamma rho C, or both rho prime.
Oh, yes.
Yani hocam aslında şurada koordinat sistemindeki değişimden dolayı.
That factor, the factor gamma arises because of the changes in the coordinates in the Dirac delta.
Peki onu şu küçük charge density için de söyleyebilir miyiz aslında oradaki?
But you see, there you have a finite volume. The factor gamma arises because of the contraction of the volume. So if you want to specify the volume, you need to use step functions. And step functions doesn't have this property. You see, theta of gamma, or let's say theta of x minus x0 over gamma, this is equal to theta of x minus x0. There is no multiplication or division by gamma. So there, the only reason why we get this factor gamma is due to the volume is now smaller. Or if you like that, given that very small volume charge, you can just treat it as a sum of point charges. And each one of the charge density corresponding to each one of these point charges acquires this factor gamma, whichever one you want. Whichever interpretation you like. Well, you see, your friend was kind of complaining, okay, here for a point charge we get this gamma because of the Dirac deltas, because there is a coordinate change. Why don't we get that gamma, additional gamma factors in the case of a finite but small volume? And my claim is we are getting that additional factor of gamma, but there is just one that such factor gamma which comes from the Lorentz contraction. which arises due to this change in the coordinates. And there is no additional gamma factor, like in the case of the point charge, because there are no Dirac delta functions there. At most, you have step functions to specify your volume, but step functions do not get that additional gamma factor.
O zaman değişmez mi yani akım? Sonuçta sadece C Y yönünde ama şey değişiyor.
Well, you see, you're saying that, let's say we have a current density running in that direction. A finite width? I don't, for me, no. Okay, infinite straight wire, zero thickness. The current is a finite thickness. Okay, the current is in the upward direction. The current density is in the z direction. It depends on distance from the center, and it's in the y-hat direction. What is the, okay, so let me just use S. What is the charge density? Is there a charge density anywhere?
Böyle bir şey olsa charge density değişiyor. Merkezden dışarı doğru.
Well, let's look at this one. No accumulation of charges. Okay, first let me ask, what is the divergence of this thing? You see, we have this equation, divergence of J plus del rho by del T. This should always be equal to 0 because of charge conservation. Now, del rho by del T plus the divergence of that thing is, there's only the y component, so del J by del Y, this should be equal to 0. Or del rho by del T, this should be equal to minus y over S J prime. So rho cannot be 0. That is one thing. You cannot have a time-independent charge density and have a uniform current in the J direction. No, first let's put a framework which is consistent. You see, if you want to have rho 0, one way is to assume that J is uniform, no S dependence. If there is S dependence, you cannot set rho equal to 0. So which one would you like to proceed with? Would you? Okay, so let's see. Then you are saying that rho should be minus y over S T J. No. J prime of S.
J prime derivatif bir şey mi?
Sorry. J Sorry. Okay, S is over here, square root of x squared plus z squared. So there is no y dependence. So you can have rho is equal to 0, no problem with that. Now, in a different reference frame, C rho prime will be gamma C rho minus V over C Jx. J prime x is gamma Jx minus V rho. Jy prime is equal to Jy, Jz prime is equal to Jz. So what will be the rho prime minus gamma V over C? Yes. Rho is 0, Jx is 0, this is 0. Jx prime will be, well, Jx is 0, rho is 0. Jy prime is Jy, Jz prime is Jz. Jz is also 0. This is equal to Js. You see, S, of course, but if you want to write Jy prime at the point S prime, this is equal to J at the point S. You have to find also the relate how S and S prime are related. You have to also make that build that relation. S is the S in the initial reference frame. So you have to replace this with a function of S prime, which is the S prime in the other reference frame.
Ama iş yönünde giderken, yani şu iş yönünde giderken sonuçta iş yönünde de akım olmayacak.
Let's see. Okay, the charges, you are saying that, let's look at the current passing such an area as we are moving. Will there be what is the number of charges that passes through my area as my wire is moving? Rho is 0. No, you see, look at this one. Rho is 0. Rho is still 0. So as this is moving, let's say take such an area, the total number of charges passing through this area, will it be 0 or non-zero? If the sum is 0, then the current density is 0. So, density doesn't change, the charge density is still 0. You see, the current density, I mean, if you want, you can just divide your current density into positive and negative charges, let's say. In one frame, it's just the positive charges that are moving upward. Okay, let's say the negative charges are at rest. The total positive plus the negative charges, it's 0. If you go to a different reference frame, the positive charges are moving in this direction. The negative charges are moving in this direction. So the positive charges creates a current in the horizontal direction, as you expect. The negative charges are creating a current in the opposite direction. The total current just turns out to be 0.
O zaman geçen yük sayısı sıfır mı?
No, there is still current in the vertical direction.
Ama bu dediğimiz alandan geçen, alanın içinden geçen.
Yeah, they cancel each other. You see, the only way if you want to obtain a current in the horizontal direction also, Jx is 0 if there is a rho. If there is a non-zero, non-trivial rho inside your wire, in that case you create a current in the horizontal direction also.
Rho'nun sıfır olmadığı zamanlarda değişiyor.
Hmm?
Rho'nun sıfır
Sure.
olmadığı.
These are the expressions we have.
Biz aslında şu an tensör analizi mi yaptık?
You see, tensor analysis is something else. We are using some results from tensors to describe our system, that's it. We don't need all the machinery of tensor analysis. This much is enough for us.
So you may ask a question. When you have current, how is charge densities equal to zero? When you have current, it means we have charge density.
Sure.
Why is
There,
charge-
okay, you see, when we have a current density, we have some moving charges. Neutral systems means we have equal amounts of positive and negative charges. But rho is equal to 0 doesn't tell us that the positive and negative charges, they are moving at the same speed, same velocity. If they are moving at different velocities, they will create different currents, and the sum need not be 0. For example, if you have take this wire. Negative charges are moving in one direction, the positive charges are at rest. So negative charges create a current opposite to the direction that they are moving. So there is a net current. The total number of negative and positive charges is 0. The system is neutral. But nevertheless, there is a non-zero current.
Peki hocam ben bu tarafa doğru hareket etsem, negatif yükler de zaten bu tarafa hareket ediyor. Pozitif yükler de bu tarafa hareket etmeye başlayacak.
Okay. Their velocities will be different. So they will create currents, maybe in opposite directions. The sum will be non-zero. Now let's look at this thing. We said that del rho by del t plus del dot j, this should be equal to 0. This is current conservation. Del rho c by del ct plus del ji by del xi, this should be equal to 0. Let me call this j0, this whole object, or j mu is equal to rho c and j. So this is j0, derivative with respect to x0, plus derivative of ji with respect to xi. But this is nothing but del j mu by del x mu. This should be equal to 0. So this is kind of how we can express the charge conservation in the four-component form. This is, in a sense, the generalization of the divergence to 4 dimensions. This is the divergence in 3 dimensions. This is the 4th dimension. Now let me look at the electric field. the x component of the electric field. Well, this is equal to minus del phi by del x minus del ax by del t. This is equal to now let me keep it like that. This is equal to minus del phi by del x1 minus del c times ax divided by del c times t, or x0. Now, F01,
Hocam ters olmadı mı?
why?
Del C phi or del x0.
You see, electric field is minus the gradient minus del A by del T. Now, F01 is Ex over C in terms of the potentials. This is equal to minus del over del x1 phi c minus derivative of ax by del x0.
Burada niye böyle yazıyor?
Oh, sorry, this is phi over c. I divided by c everywhere. Minus or plus del over del x1 minus phi over c minus del over del x, sorry, this is x1, this is x0 of a of 1. Which is equal to del over del x1 phi over c plus del over del x0 a1. Now what did I do over here? Oh, this is x1. Well, it was upper index. I lowered it. The one component doesn't change sign. This was an upper index. I lowered it. The zero component changes its sign. Which one? Yeah, this minus one is still over here. That minus one is over there. I mean, this can go up or down, it doesn't change. Well, I'm just defining A1 to be AX. So F01, this is equal to minus or plus del over del x0 A1 minus del over del x1. Let me call that A0.
Hocam A1 nasıl var sorunlu eksiltme?
It's not A1, it is x0. We change its sign. Here, 0 is an upper index. This is a covariant vector. Here, this is a contravariant vector. Now, the reason why I lowered them is you see both 0 and 1s, they are covariant indices. Derivative with a contravariant index is actually a covariant index. So that's why I lowered it. In a sense, the technical detail for the time being. And now I define A for vector as phi over C and A. Now, of course, I still need to show that this is a 4 vector, but for the time being, let's just use that notation, and then eventually we will show that it's a 4 vector. Well, this looks nice. Derivative with respect to the first index of the potential with the second index minus derivative with respect to the second index of the potential with respect to the first index. At least for F01, there seems to be such a definition. Now the task is, what about the other ones? One is 0, F02, F12, F13, and we will actually show that F mu nu, in terms of the potentials, is del over del x mu A nu minus del over del x nu A mu. In terms of the potential, it has such a nice, simple, symmetrical form.
Bu yazdığınız total potential mi olur? A dediğiniz.
The vector potential. Anyway, we will continue, pick it up from here on Friday.
Peki bunu G içinde yazacak mıyız?
Anyway, these are for Friday. And there won't be any, I won't be coming for the recitation on Wednesday, because basically on Friday, what is left is, we'll just take 1 hour, and then we can discuss questions. So I'll see you on Friday.